Hello again. This video is designed to complement Khanacademy's video on radiocarbon dating, and Sal gave us an example where we have a sample of bone, for instance, and in Australia significant finds have been dated back to up to 30,000 years, Aboriginal remains, remains of campfires, remains of or rock paintings, that sort of thing. Imagine we have a bone sample, and from that bone sample we get 34 grams of carbon. And of course, the bone's not purely made of carbon. We're going to use this for simplicity's sake. We're going to say it's all carbon. And then, of course, by radiocarbon dating, we can measure its activity, and we do that and find that this has activity of 0.920 becquerels, and 1 becquerel is equal to 1 decay per second. Okay, so we've got just under that, just under 1 decay per second from this 34 grams of carbon, and so we can compare this to modern life. So this organism, whatever it may have been, died many hundreds or thousands of years ago, and stopped taking in carbon-14. And we know that organisms today, so an organism still alive today, the carbon in its cells has an activity of 0.226 becquerels per gram, and so we can compare these two and work out how old this sample is, knowing that carbon-14 has a half-life, and that can be represented by T and a subscript half equal to 5,730 years. Okay, so we've got 0.920 counts per second, and activity of 34 grams. So 34 grams is 34 multiplied by 0.226, which equals 34.226, 7.684 becquerels per 34 grams, and that's a living organism today. What the activity that organism would have. So the count rate, we can compare it to the original, to our 0.920 becquerels from this 34 grams. So 0.920 as a ratio, 7.684, which is equal to 0.920 divided by 7.684, 0.12, okay, of its original value. That's its activity. And that's like saying 12% of its original value. Okay, so we know this equation, N is equal to N subscript 0 over 2 to the power of N, which, and this is the, this here, I'll do this in a different color, that is, this is how many atoms left to decay. This is N0 is of course the original number of atoms. And this little n is number of half-lives. Okay, so we can rearrange this equation easy enough. Change colour here. Blue's a bit hard to see, and we'll go yellow. Okay. N is equal to N0 multiplied by 1 on 2 to the n. Simple mathematics there. And we know that n, the ratio of number left to decay over the original value is equal to 12%, 0.12. So that leaves us with 1 on 2 to the power of n is equal to 0.12. And we can rearrange that, swap these two over, easy enough, simple mathematics. 1 on 0.12 is equal to 2 to the power of n, and 1 over 0.12 is equal to 8.33. I've already done this calculation. Okay, so 2 to the power of n is equal to 8.33, and I'll just go across here so we can use a bit more of this page here. We take the log of this, log of both sides of the equal sign, and an exponential identity is just n log 2 equals log of 8.33, and so then we can rearrange that for n equals to log 8.33 over log 2, and I've done that calculation already. That's equal to 3.06. Now what does this number mean? That's half-lives there. We've calculated the number of half-lives, and we talked about that a little bit earlier. That's our half-life there, that little lowercase n. So equal to 3.06, and we know that carbon-14 half-life equal to 5730 years. So we've got 3.06 half-lives multiplied by 5,730 years equal to 17,700 years old is our sample. So the only problem with this, and the next video is going to show something different, how it's more commonly done, because there's an issue with how do you get 34 grams of a sample that's obviously quite rare. It can be valuable, it can be a historic artifact. We don't want to ever use 34 grams, we only use milligrams. And you can't, in order to get the number of the activity of carbon-14 in a sample that is of the value of milligrams takes a long time. You'd have to be measuring that activity for a long time, because 5,730 years, this half-life is quite long, and so you're not going to get a real value for the activity, because we don't know when any one atom is going to decay. And in 1 second you might get 1 decay. In the next 10 seconds you might get 0 decays. So there's got to be a better way that you can use smaller samples than 34 grams, and there is a way, and I'll show you that in the next video. Thank you for watching.